So let's do a one-shot video on hydrocarbons, starting with preparation methods of alkanes. Here, first one is hydrogenation of unsaturated compounds. Here, as you can see the example, CH2 having double bond, that is ethene. On reacting with hydrogen, we will get CH3, that is ethane, right? And in the presence of nickel, platinum or palladium. Second is Woods reaction, and here the reagent is dry ether. Okay, here the general form is written as you can see, that is 2Rx plus 2Na in presence of dry ether will give me my alkane, that is RR plus 2NaX. Example also is written, you can have a look. Coming to the third one, reduction of alkyl halides, that is Rx plus 2H. Okay, here I am adding hydrogen atoms, 2 hydrogen atoms, while in hydrogenation, we added hydrogen molecule, right, H2. So here the reagents are LiAlH4, or you can use NaBH4 or zinc CH3COH, zinc in the presence of CH3COH, right? So what you will get is RH plus HX. Simple example we will take, that is CH3CH2Cl, right? On reacting it with 2 atoms of hydrogen, in the presence of LiAlH4, we will get CH3 plus HCl. That is our alkane, that is ethane plus HCl. So here are the reagents that you can remember. Coming to coal-based electrolysis. So here we learned about RCONA. First, electrolysis. First step is ionization, right? So of RCONA, we'll ionize it. Na is plus, so RCOO minus. Okay, the next step, reacting it with water, right? Electrolysis. So reacting it with water, we'll get 2 moles of RCONA. Reacting it with 2 moles of H2O, we'll get RR, that is we got our alkane, plus 2 moles of CO2, and this will obtain at the anode, but at cathode we'll get 2 moles of NaOH plus H2 in gaseous form. Okay, or emission, right? Emission takes place, so we are putting that arrow upwards. Now at anode, what happens? Oxidation takes place. So what is in the form of oxidation? It is losing of electrons, right? Oxidation involves losing of electrons, right? So RCOO minus will lose 1 electron and become RCOO radical. That is, that small dot is known as radical. So RCOO radical will become, again, it will form CO2 in emission form, that is gaseous form, and R radical. Okay, that is our alkyl radical. So if I add 2 alkyl radicals, so in homolytic fission, we know that when we add 2 radicals, we can get a bond, right? So here we will get an alkane, right? Bond between 2 alkyl radicals. Okay. So, and we'll also get CO2. So the final products we get are RR and 2 moles of CO2. So coming to cathode, what we'll get at cathode? Cathode having reduction. So what is reduction? Addition of electrons, right? Accepting of electrons. So 2H2O plus 2 electrons, that is accepting of 2 electrons. What it will give us? It will give us 2 moles of OH minus plus 2 moles of H2 in gaseous form. That is emission, right? Now again, next step we are left over with sodium plus, right? Sodium plus cation plus OH minus, right? So it will give us 2 moles of NaOH. So here we got all our products. Now coming to 5th one, that is decarboxylation. So carboxylation, CO2, decarboxylation, removal of CO2. Okay, so RCOONA in the presence of NaOH and CaO, which is also known as soda lime, will give us RH, that is our alkane, plus Na2CO3. Okay, here we have a simple example, CH3COONA. In the presence of NaOH and CaO, that is soda lime, it will give us CH4, that is methane, plus Na2CO3. 6th is Core-House synthesis. So here we have dialkyl lithium cuprate with us, right? It will react with our alkyl halide So R and R dash, we have two different types of alkyl groups here, right? So R and R dash will get one alkane group plus RCU plus LIX. So this is the reaction. So for example, if we take CH3, CH3 whole twice because it is dialkyl, right? And CuLi as normal. So this is my first R. What is my second R? That is R dash. It is CH3, CH2. Yeah, it is CH3, CH2 as you can see here. Now this is with chlorine, right? Here the X halogen is chlorine. So what we'll get? Just merge these alkyl groups. So we'll get CH3, CH3 with CH2, CH3. And the leftover, that is HCl. Okay. Now coming to the seventh one, which is Grignard's reagent. Okay, formation of alkane using Grignard's reagent. So the reagent is RMgX. That is alkyl magnesium halide. Okay, plus H2O water will give us RH plus MgOH. Okay, so here I can use H2O, NH3, COOH, ROH or RNH2, right? So for example, if I take that is this compound with MgBr plus H2O will give me CH3 plus MgOH Okay. So this, as you can see here, we have one carbon. So we got ethane here. Okay. Now the last one, that is the eighth one, is using metal carbides. Okay. Using metal carbides. Yeah. So using metal carbides, example is aluminium. Okay, aluminium carbide, that is Al4C3 plus 12H2O giving CH4 3CH4 plus 4AlOH thrice. And the second example is Be2C plus 4H2O giving CH4 plus 2BeOH twice. So here we are done with the preparation methods of alkanes. So this is the whole mind map. You can refer this as well. Coming to alkenes. Okay, now preparation method of alkenes. First is dehydrohalogenation. So if you want in detail the preparation methods as well as the chemical properties as well as physical properties of alkanes. So we already had a video yesterday. So I'll just post the link in the description box. So here we have for alkenes now, right? ENE. So the first is dehydrohalogenation. So here you need to remember the reagent alcoholic KOH, right? Potassium hydroxide. Here from this compound, we will firstly remove hydrogen as well as the halogen, that is chlorine here, right? So when we remove this hydrogen as well as chlorine, we are left with CH2, but carbon valency is not satisfying. So we'll have double bonds like this. So this CH2 and this CH2 will have double bonds here. Okay, and the leftover, because we have Cl here, right? This Cl and this H will form HCl. Okay, so the reaction goes like this. So here the important point to remember is alcoholic KOH for dehydrohalogenation. Okay. Second is just dehalogenation. Okay, removing of the halogen. So for example, CH2, okay, CH2Br, right? So how to remove these halogens? By using zinc dust. Here the reagent is zinc dust. We will get simple again ethene, right? So the simplest example is ethene we have used in many cases, right? So third is dehydration. So you can just break down. First was dehydrohalogenation, second dehalogenation, and third is dehydration. Okay, so dehydration, as we know, it is removal of water molecule, right? So for this, we'll use concentrated H2SO4 or we can use alumina, that is Al2O3. Okay, here you can see it. It has been written. So CH2H, okay, so actually it's CH3 and CH2 with OH. Okay, when I react it with the presence of concentrated H2SO4, I'll get again that simple ethene. The fourth one is partial hydrogenation of alkynes. Okay, hydrogenation of alkynes, adding hydrogen to alkynes, partial form. If it is full, then it will give me the end product as alkane. But I want alkene, so it is partial, right? So carbon-carbon triple bond, I'll add H2. So this H2, one H will get added to this carbon atom, one H will get added to this carbon atom, breaking one bond and getting only double bonds between these two carbon atoms. Okay, so we also have examples over here. Yeah. So example is CH3, C triple bond C, again CH3. So here the reagents are Lindlar's catalyst or Li or Na you can use, and with liquid NH3. So here are the reagents. As you can see with the arrow, right? So if we take Lindlar's catalyst, we will get cis isomer. That is, we will get same type of molecules on the same side, right? On the first example, you can see I have used Lindlar's catalyst, that is palladium with BaSO4 and quinoline, right? So I'm getting CH3 both upwards on the same side, and HH, that is hydrogen, both downwards on the same side, right? So this is known as a cis isomer. So what is the opposite? It's trans isomer. Okay, that is, you will get the same molecules on the opposite sides, right? Here you can see opposite sides we are getting HH and CH3. Over here, right? Opposite sides we are getting CH3 and CH3. So this is a trans isomer. So when I'll get a trans isomer, when I react a triple bound carbon compound with Li, that is lithium or sodium, with liquid NH3, right? Now, coming to the mechanism. So how does this work? Okay, starting with the first thing, CH3, CH2OH, right? So firstly, we are going to remove the water, right? Concentrated H2SO4, right? So I'll just erase these. Yeah. So firstly, the first process is protonation, right? So what is protonation? It is addition of proton, that is hydrogen, right? Hydrogen having atomic number 1, right? So it is protonation. Addition of hydrogen is known as protonation. That is the first step. Second step is removal of water molecule. As you can see, when I added this protonation, as you can see here in the OH, right? In OH, there are 2 lone pairs around oxygen, right? So with the help of these 2 lone pairs, I'll add hydrogen, right? I'll do the process of protonation. So after that, what will happen? After that, what will happen? We will get H2, of course, right? And 1 lone pair will get vanished. That is, we will get a plus charge on oxygen. We'll get a plus charge on oxygen. This you can see over here, right? So this plus charge, what we'll do? We got H2O, right? So we'll remove that H2O now. Okay. So when I remove this H2O, what will happen? This plus charge will shift on the nearby carbon atom. So it has been shifted here, as you can see. So here what I'll do now, here I have C plus H2, that is carbocation, right? So what I will do here, in the neighboring carbon, I have 2 hydrogen atoms, right? Here you can see with a single bond, right? So I will do a hydride shift, right? That I'll take this hydrogen here. So what will happen? This plus charge will get shifted on this carbon atom, on the neighboring carbon atom, right? It has borrowed hydrogen, so the plus charge is being shifted. So what will happen? Here you will get a plus charge and you will get CH3 in the outer side. Okay. So now finally what will happen with this CH3 at the end, that is CH3, CH2. In the middle we will have with the plus charge CH and CH3. With this what we'll do? We will do deprotonation. That is removal of H or hydrogen atom. Okay, so after doing deprotonation, yeah. So after doing deprotonation, what we'll get? This plus charge will get vanished off, and then we will get a double bond instead of the plus charge. Okay, so this is the product form. In a similar way, we can also do for one more compound. I'll just erase these. Yeah. So one more compound we are having, that is CH3. Okay, CH3, CH3. Okay, CH2 and OH, as you can see this one. Again, repeating the same process, we'll do protonation, addition of hydrogen. So we'll get H2O molecule with a plus charge. So to remove, we have to remove that H2O molecule. So the plus charge will get shifted, right? So when I remove this H2O molecule, plus charge is shifted, right? So then what will I do? This plus charge I'm having on this carbon atom, right? So here, but the problem is that we don't have any hydrogen atom to shift the plus charge again, right? Why? Because the compound is like this, C, and here we have that carbocation, that is C plus H2, CH2 plus, right? So we don't have any hydrogen to remove this plus sign. So what we'll do here? Here we will do methyl shift. The whole methyl, that is here, we will shift this methyl over here. Of course, this plus charge will get shifted to the middle carbon atom. Okay, so the same steps you can see over here. This one. So we have plus charge on the middle carbon atom. So again, to remove the plus charge, we'll apply deprotonation. Okay, so after doing deprotonation, what we'll get, instead of that plus charge on the same place, we'll get a double bond, right? So here you can see this is the final product. This is the final product. Okay, now coming to the next thing, that is preparation methods of alkynes. So till now what we saw the preparation methods of alkanes, right? So there we had eight methods. Then the next one we saw preparation methods of alkenes and also the mechanism of how partial hydrogenation takes place, right? And the third we are going to see the preparation methods of alkynes. So the first one is dehydrohalogenation again of vicinal dihalides. So what is vicinal? Vicinal dihalides means that the halides are attached to adjacent carbon atoms, okay, side by side carbon atoms. So it is known as vicinal dihalides. So here, as you can see, we have CH and both are adjacent, right? Both are side by side, and to that halides are attached, that is X group, right? So here I'll take alcoholic KOH and HX, right? The halide HX. So what I'll get? We'll take the pen. Yeah. So what I'll get here? So the first step I'm getting is I'll remove this halogen and I'll remove this hydrogen, right? So I'm getting a double bond first of all. So in the first step, I'm getting a double bond. So further, when I react it with NaNH2, I'll get a triple bond. So this is dehydrohalogenation. Here it is a bit lengthier as compared to alkenes, right? So here you need to remember firstly alcoholic KOH and then NaNH2. You can simply do it in one step also, alcoholic KOH and writing here directly NaNH2. So of course from directly this step you can jump to the last step. Yeah. Now coming to the next one, that is dehalogenation of 1,1, 2,2 tetrahaloalkanes. Okay, tetra 4 halo, that is halogen group, right? Here you can see X, 4 are there. 4 halogen groups are present to the same adjacent carbon atoms, right? So which is This position is 1, right? This position is 1 if I assume, and this position is 2. Okay, it doesn't matter because on the both sides it's symmetrical, right? It is symmetrical compound. So here, if I assume it 1, so 1 comma 1 because 2 positions, 2 comma 2 again, two halogen atoms, right? 1 comma 1, 2 comma 2, tetrahaloalkanes. So dehalogenation, removing of those halogens. So again, when I remove these halogens in the presence of zinc dust, I'll get triple bond between the carbon atoms. So the third is from chloroform. Okay, so what is chloroform? It is CH3Cl plus 6Ag. It is a simple reaction. You just need to remember this reaction, that is 2CH3Cl plus 6Ag giving CH2CH triple bond CH plus 6AgCl. So this is triple bond. Okay, so simple reaction using chloroform. Okay, so this is chloroform. So silver is just displacing this methyl group with chlorine. Okay, you can just remember it as a simple displacement reaction if it is better understood like that. Okay, so fourth is from carbides. Okay, so from carbides, that is CaC2. Okay, it is CaC2. Okay, CaC2 plus water, that is H2O, giving CH triple bond CH plus CaOH twice. Okay, so we are getting ethyl and calcium hydroxide. So similarly, if I do it with Mg2C3 plus H2O, I'll get the same, that is, but here there are 3 carbon atoms, right? So CH triple bond C, and with that single bond CH3 plus 2 MgOH twice. So these were all the preparation methods of alkynes. Okay, the 4 methods, that is dehydrohalogenation. Here you need to remember alcoholic KOH and NaNH2. And the next one is dehalogenation. Here you need to remember zinc dust. And third one is chloroform. Here you can just remember it as a displacement reaction. And fourth one is from using carbides. Okay, so these are the 4 preparation methods of alkynes. So till now we saw preparation methods of alkanes, and then we saw the preparation methods of alkenes, and then we saw preparation methods of alkynes as well. Now going to the next topic, that is chemical properties. So the first one is alkanes. In alkanes, the first chemical property is halogenation, as we discussed in the last video itself, right? CH4 plus Cl2 in presence of sunlight, it will give CH3Cl plus HCl, right? So you can go through this free radical chlorination of methane, right? First is chain initiation. So here Cl2, what you have to do? Initialize the chain. That is, you need to break the chain here, right? Cl bond you need to break, and you want the free radical, chlorine free radical, okay, by using homolytic fission, right? Now what is homolytic fission? If I have chlorine bond like this, and I will do homolytic fission, then this bond will break half like this and half. This is the representation of homolytic fission, which will give me chlorine free radical. This dot represents free radical. Okay, the second one is chain propagation, that is CH4 plus chlorine free radical giving CH3 radical, that is methyl free radical plus HCl. Okay, now this methyl free radical reacting with chlorine molecule will give me CH3Cl, again one chlorine free radical. Next is chain termination. So terminating all the radicals and getting our final products, that is CH3 plus CH3, both are radicals, we'll get CH3 bond, that is ethane, and chlorine free radical plus chlorine free radical will get Cl2. This is the reverse process of initialization, right? Initiation. Then the third is CH3, that is methyl free radical plus chlorine free radical will give us CH3Cl. Coming to the next one, that is aromatization. Here, we are converting non-aromatic compounds to aromatic compounds. Okay, so here example is for hexane. Okay, and the conditions are you have to use Al2O3 or Cr2O3 in the temperature 600 degrees Celsius and pressure that is 15 atm. So here in the box it is written, you need to remember this. Okay, so here that is hexane, simple benzene ring I'll get. Okay, so this is the benzene ring. Okay, this circle represents the double bonds, alternative double bonds. Okay, now coming to the third one, that is isomerization. The name itself says what we will do in this reaction, right? So butane, we have butane. In the presence of anhydrous AlCl3, it will get converted to its isomer, that is 2-methyl propane. So here you can count the number of carbon atoms are same, that is 4, right? Coming to the fourth one, that is pyrolysis or cracking. The name itself suggests cracking of that carbon chain in the presence of heat. Okay, so as you can see here, this also we discussed in our last video. See, 1, 2, 3, 1, 2, 3. So if I crack it over here, so as you can see, in each of my processes, I have 3 plus here 3, right? So here what I did, I got CH3, CH2 and CH2 radical. Why? Because I broke a bond. So I'll get 2 radicals again, right? Homolytic fission that we just saw. Okay, so homolytic fission, with that we'll get 2 radicals, okay, in separate bonds, right? So first is CH3, CH2 and a free radical of CH2 plus the free radical plus CH2, CH3. So in the first process, what I'll do, this radical, I'll convert it into a bond over here. So I'll simply get a double bond, that is propene. And here what I'll do, here I'll add one hydrogen radical. So what it will happen, this hydrogen radical will go and get added to this. So two radicals together will make a bond. So I'll get CH3, CH2, CH3. So I'll get propene as well as propane. So cracking or pyrolysis will give us propene as well as propane. Means what? The cracking or pyrolysis of alkanes will give us alkenes as well as alkanes. Okay. Coming to nitration. So the name itself suggests nitration related with nitric acid. Okay. So reaction in the presence of concentrated nitric acid. Okay. So CH3, CH2, CH3. So reacting it with concentrated HNO3, we'll get CH3, CH2. Here again CH2 and NO2. Okay, so this is nitropropane. Now coming to sulfonation related with sulfur, sulfuric acid, right? So CH3 will, in the presence of concentrated H2SO4, we'll get same. In the above reaction, we added NO2. Here we'll add SO3H, which is a functional group, right? Sulfonic acid group. Now coming to seventh one, which is combustion. General formula of combustion of alkanes is CnH2n plus 2 plus the coefficient of oxygen molecule is 3n plus 1 by 2 and NCO2 plus n plus 1 H2O. For example, I have taken combustion of methane, that is CH4 plus 2O2 giving CO2 plus 2H2O. Okay. So this was all about alkanes. So how do we remember these all 7 chemical properties? You can just use this kind of word or any remembering technique, as you can say, and it is that SAPHNIC. Okay, something like Safnic. You can pronounce it like that. You just need to remember this word Safnic and alkane. Okay, because alkane, if you don't remember, then it's difficult. Okay, so alkane and Safnic. What is Safnic? Chemical properties. Okay, stands for sulfonation, A stands for aromatization, P stands for pyrolysis, right? And yeah, P stands for pyrolysis, wherein H stands for the first one, which is hydrogenation. N stands for nitration. I stands for isomerization and C stands for combustion. So pyrolysis I have taken, not cracking. I have taken pyrolysis P. Okay. So coming to alkenes now. So for alkenes, how many processes do we have? Again 7. Okay. So first is hydrogenation, that is addition of hydrogen. Okay. Again in the presence of nickel, platinum or palladium. Okay. So CH2 plus 2 moles of hydrogen atom. In the presence of nickel or platinum or palladium, you will get CH3, that is alkane. Okay, second is halogenation of vicinal dihalides. Just now we discussed what was vicinal dihalides, right? So CH2 again, that alkene plus chlorine, right? Any halogen you can take in presence of CCl4. So this is very, very important in addition of halogen or halogenation, that is CCl4, right? You can just make a box and write it down. So third is addition of hydrogen halide, right? Hydrogen halide, break it down. Hydrogen H, halide X, right? So again, we're doing it for alkene. So CH2 double bond CH2, the simplest alkene we are taking, right? So CH2 double bond CH2, the simplest alkene, plus HX, that is hydrogen halide, will give us CH3CH2X, right? The simplest example is CH3 CH double bond CH2 plus HBr, right? Will give us here the halogen, that halide is bromine. Okay, so it will give us CH3 CHBr and CH3. So here bromine, we'll get two kinds of products, that is bromine is attached to the middle carbon or it is attached to any one end. Okay, any one end we attach, we'll get the same name. So don't need to write attached from the right side or left side. Okay, so the major product is attached from the between or the middle carbon. Okay, now what is the mechanism? So the mechanism for addition of hydrogen halide goes like this side, as you can see. So here I have CH3 CH double bond CH2, this thing which we had taken as an example, right? So here we are again doing protonation, addition of proton. So with this protonation, what will happen? This double bond will break and here I'll get CH3. While here I got a plus charge. The plus charge is shifted to the carbon while the hydrogen is shifted to this, right? The last methyl group, right? CH3. It will become methyl group. Okay. So here I'll add my halogen. Okay. Here we have used bromine. So we are adding bromine, right? So after adding bromine, it will become CH3 CHBr, adding bromine to the middle carbon atom, and we'll get CH3. So this, the plus sign in the middle of the middle carbon chain, okay, middle carbon, it is more stable. Why? Because it is primary carbon atom, right? It is secondary. Secondary means what? Carbon atom connected to two different carbon atoms, secondary carbon atom, right? While if we compare to the second, that is the minor product, here you can see the plus charge is shifted to the end, right? End carbon, which is a primary carbon atom connected to only one carbon, right? So it is less stable and it is minor product. And adding Br here will give Br at the end. Okay, so these were the two possible products in which one is more stable and major, one is less stable and minor. Okay, coming to the next one, which is addition of H2O, that is water. Okay, addition of H2O, that is water. So again, we'll take our alkene plus water in the presence of H2SO4, which is dehydrating agent, will give us CH3CH2OH, which is ethanol, right? So the next example we have here, that is butene, right? So but1ene or butene plus H2O will give us 2-butanol, right? So at this place, OH is attached to butanol. Okay. So the fifth one is ozonalysis. So ozone, as we know, it is O3, right? So again, we have our ethene. So reacting it with ozone, this structure is formed. I'll just make a circle or a cloud for it. So this kind of structure is formed. That is, the two R or alkyl groups are separated by oxygen atoms, 3 oxygen atoms in this form. So this form is called ozonide. Okay, so when I react this ozonide with zinc, H2O and H2O2, I'll get 2HCHO. How I'll get 2HCHO? Just breaking this ozonide. So how will we break? We'll break it in this way. So we will get one H will come out, that is H. So we are left with CHO, right? CHO, HCHO. And again, this side also we'll get the same products. So we'll write simply 2HCHO. So similarly, doing one more example, here we have CH3, single bond CH, double bond CH2. So wherever you find double bond, quickly draw those oxygen molecules. Okay, and your reagent should be O3, zinc and H2O. Okay, to make it shorten. Okay, so above we saw a 3-step reaction or 2-step reaction. Here it is just a 1-step reaction, right? So here O3 and zinc and H2O, right? So here I saw this double bond, so I quickly drew the oxygen atoms, right? So here oxygen, again I'll break it down like this, right? So what we'll get? One is our normal HCHO, right? Because we have CH2 here. What is the other product? The other product formed is this CH3 would be as it is CH3, CH and this O. This O. Okay. So this is ozonalysis. Now coming to the next one, that is oxidation of alkenes. So oxidation, as we know, addition of oxygen, right? So CH2, that is our alkene, plus H2O plus O2 in presence of alkaline KMnO4 and in particular temperature of 273 Kelvin, that is 0 degrees Celsius, it will give us CH2OH with a bonding of single bond CH2OH. Okay, so if we take one example, we'll get here, I have taken the example of propene, right? Prop1ene or propene, and reacting it with H2O plus O. You can write it in this way also, above the arrow H2O plus O, and below the arrow alkaline KMnO4, temperature 0 degrees Celsius or 273 Kelvin. So you will get OH and OH atoms wherever the double bond was present. Okay, so here you need to remember alkaline KMnO4 plus 273 Kelvin or 0 degrees Celsius. So polymerization is the last one, which is NCH2CH2. At high temperature, it would become CH2, single bond CH2 with the base N. Okay, so which is polythene or polyethene, right? So how to remember these now? So again, for this also we have a shortcut method. So here it is HH, H2, H2O and OOPS, that is OOP, wherein HH is halogenation and hydrogenation. Then next was H2, right, which is hydrogen halide, right? And the next is H2O, that is addition of H2O. Then OOPS, that is O, first O stands for ozonalysis, second O stands for oxidation, and P stands for polymerization. So HH, H2, H2O, OOPS is the remembering point, okay, for alkenes. Now coming to the next thing, that is for alkynes. So for alkynes, we just have two of them, chemical properties. First is the acidic nature. So terminal alkynes are more acidic in nature, the first point. Second point is percentage S character is directly proportional to electronegativity, which is again directly proportional to the acidic property. Okay, percentage S character, as we know, hybridization, sp3, sp2, right? And the second one is polymerization or aromatization. So 3CH, triple bond CH, in the presence of RHT, that is red hot tube, in that present is iron, at 763 Kelvin will give us benzene. So these were the two chemical properties of alkynes. Now let's come back to the next topic, that is we have the double bond equivalent or degree of unsaturation. So what is degree of unsaturation? So the number of H2 molecules required to convert unsaturated compounds into saturated compounds, that is alkynes or alkenes into alkanes. Okay, so the simple example, first one, CH2, CH2. How will we convert it into alkane or single bond, right? Single bond carbon compound. So we have to add hydrogen atoms. So here, if I add one hydrogen molecule, that is 2 atoms, I'll get, of course, my CH3 single bond CH3, right? Then coming to the next example. So here my question was like this, right, which is pentane, but I have double bonds as well at the positions 1 and 3, right? Okay, so 1 and 3. So if like this we count, it is pent 1, 3 diene, right? So here, if I want to convert this alkene into alkane, what I have to do? I want here one hydrogen atom, right? Here as I have written, here I'll need one hydrogen atom. Here also I'll need one hydrogen atom. Here and here. So totally 4 hydrogen atoms I'll need. So these 4 hydrogen atoms means what? I can write them as 2 H2 molecules, right? So the degree of unsaturation is 2. So coming to the next one. The next example, yeah, is this structure. So for this structure, I have one double bond over here, right? And one double bond with oxygen, right? So again, for one oxygen, I'll need 2 hydrogen atoms here. Again, here one hydrogen, here one hydrogen. Now, to break that cyclic compound, I'll also need one hydrogen molecule, that is 2 hydrogen atoms. So in total, how many molecules do I need? One for breaking the cyclic compound, one for that double bond over here, and one for the double bond between oxygen and that ring, right? So total 3. Next one, coming to the next one, that is benzene attached to COOH. Okay, so COOH, I can write it in the form of C double bond O and OH, right? Again, to break the double bond, one molecule. To break the cyclic chain, one molecule. Now I have 3 double bonds inside. So of course 3 more molecules. So 2 plus 3, that is 5 total molecules, or the degree of unsaturation is 5. Now if molecules are given, right? So if we don't have structures and the chemical formula is given, then what we have to do? Then we have to apply this formula. That is Du is equal to carbon, number of carbon atoms plus 1 plus number of nitrogen atoms minus number of halogen atoms, that is X, right? Halogen can be bromine, chlorine, right? And X by 2 minus number of hydrogen atoms by 2. So here we have applied, as you can see, for example, this, right? That is C4H10O. So here carbon 4 plus 1, okay. No nitrogen atoms in this compound, no nitrogen atoms, 0. No halogen atoms, 0. Hydrogen 10. So 10 by 2 is 5. 5 minus 5, 0. Okay. So this, for this molecule, we don't need any hydrogen molecules, right? So the next one, coming to C7H7ON. So here, as you can see, we have 7 carbon atoms. Okay, 7 carbon atoms. Nitrogen atom, we have 1. So 1 by 2 plus 1 by 2. And no halogen, 0. And hydrogen 7. Okay, hydrogen 7. So we have here 7 plus 1, 8. Right, this 8 plus this minus 7 and 7 by 2 and plus 1 by 2. Right, so we'll get 8 minus 6 by 2, that is 8 minus 3. So here we will need 5 molecules, that is degree of unsaturation is 5. Coming to the next topic, that is conformational isomers. So conformational isomers, they are the isomers which arise due to free rotation around carbon-carbon single bond. Okay, that is C single bond. Okay, so they arise due to free rotation around carbon-carbon single bond. So what are we telling here? We need at least one single bond. So therefore, it is not possible for methane, right? Only one carbon is present. So no bonds only with other carbon atoms. So it is not conformational isomers are not present for methane, but they are present for ethane. Let's look at them. Ethane. So this is the structure of ethane, right? So we will describe the structure in two forms, that is the Newman projection form and Sawhorse projection. Okay, so to represent them in those projections, we'll have to take some parts. Like this carbon atom represents the backside part, which would be represented in the form of a circle. Okay, dot dot circle. And the front part would be represented in the form of dot. Right? So coming to Newman's projection, here you can see this is the front carbon atom because this is the having dot, right? So hydrogen, hydrogen. Behind that, same to that is parallel. Okay. So if we keep it like this, it wouldn't be seen. So we have just tilted it, but theta is 0 only. Okay. Angle made between them is 0 only. Okay. They both are on each other, but seeing from the front view, we can't see them like that, right? So we have just drawn it like that. So the dot dot lines are the backside ones, right? And this dot dot circle is this back part, back carbon. Okay, so when I'm rotating the back one, always remember, we'll always rotate only the back ones. Okay, so back ones, when we rotate it to 60 degree, okay, 60 degree, what will happen if I'm keeping it like this? I'll rotate it to 60 degree, right? So then you can see, right? Then you can see the bonds, right? So here the dot dot lines represent the backside bonds or the backside atoms connected to that backside carbon atom, that is this circle. Okay, so this is the Newman projection form. And when we do not tilt it, it is the eclipsed form. Tilted 60 degree is the staggered form. Now we'll understand much better with the Sawhorse projection form because actual molecule is like this, see, which is the eclipsed one. So here, this is not tilted, it is eclipsed. When we tilt it 60 degrees, right? We'll tilt it like this 60 degrees. So then what will happen? We'll have like this hydrogen atoms. Okay, so this is the back carbon which we were talking about. So this is the staggered form. So with the Sawhorse projection, we can understand it in a much better way. Okay, but of course, both the forms are important. Coming to the next one, that is propane. So just now we discussed about ethane. Coming to propane now. Propane is what? It is having 3 carbon chains, right? So the first one, that is the eclipsed form, is this one. This is the eclipsed one. Okay. Yeah. So this is the eclipsed one, which is C, of course, 3 carbon atoms, prop, and ane, that is, it is having, just a second. So it is H, H, and H. Okay. Yeah. So here we have propane. So this is the eclipsed form over here in the right side, which is named A. Again, in that we have named back and front. And here it is the staggered form over here, in which we have included CH3 bonded with this carbon atom like this. Okay. So, or we have branched it, right? We have branched this carbon. So this is the staggered form and this is the eclipsed form. Now coming to Sawhorse projection again. So here, Sawhorse projection, what do we have? We have the actual structures. That is, this staggered form we are converting into Sawhorse projections like this. CH3, H, H. Behind we have here carbon atom, right? Here we have carbon, this carbon, H, H, H. So when we rotate the behind one, we always rotate only the behind one, right? So behind one, when we rotate in 60 degrees, we'll get HH and below we'll get CH3. Okay, so this was propane. Now coming to butane. Yeah. So in butane, we have this structure. We are considering butane like this. That is C having CH3, H and H on both the sides, symmetrical, right? And this is the back carbon atom. This is the front carbon atom. Okay. In Newman projection again, circle, dot, dot, circle is the back carbon atom and the complete dot is the front carbon atom, right? So here, as you can see, here studying about Newman projection form, this is the first form. Okay, this is again fully eclipsed. That is, both of them are on each other. Okay, no degrees of rotation have been taken place. Right. Next is the staggered form or the Gaucher form. Right. Here 60 degrees rotation has been taken place. 60 degrees. Right. So we have this CH3 move to 60 degrees like this. Okay. So this is the back carbon atom. Okay, the behind circle. Now, and of course, hydrogen atoms will also move 60 degrees like this. Okay. 60 degrees. Okay. After this, we have again 60 degrees. Again, we will move it into 60 degrees. Now, what will happen? Again, it will overlap fully. Now, this time it is partially eclipsed form. This form is known as partially eclipsed form. So, here you can see this hydrogen is partially eclipsed on this one. This hydrogen is partially eclipsed on this methane, right? Methyl group, and this methyl group is partially eclipsed on this hydrogen atom, right? Or hydrogen bonding. So this is the partially eclipsed form. This is the third one. Okay. So after this, again, if we rotate, so finally this CH3, which was almost partially eclipsed on the H bond, will come here fully opposite to the CH3 of the front carbon atom, right? This is the front. While again we have to draw the circle here. Yeah, the circle behind carbon atom and front carbon atom, both the CH are now in opposite directions, right? Which means what? In Sawhorse projection, you will be able to understand it in a better way. We'll go through Sawhorse projection. Yeah. So this is the Sawhorse projection. As you can see here, the first one was normal. Okay, no rotation. Second one was 60 degrees rotation. So like this shape came. In the third one, what we did, we had again 60 degrees rotation, right? So in this 60 degrees rotation, this CH3 was parallel to this hydrogen atom. Again 60 degrees, what happened? See, now both the CH3s are in opposite directions or opposite sides, right? So this is the anti-form, right? So how can you remember this anti-form? See, many times we see, right? Some kinds of auntie is gossiping and they'll soon come to disputes or fights, right? So they fight always, so they are in opposite sides. You can remember it like that. Opposite sides, and they are more stable, right? Why they are more stable? Because they are away from each other, opposite, right? So they are away from each other, opposite, because they have quarreled and they are away from each other, so they are stable. Okay, less repulsion. See, the best word, less repulsion when they are away from each other. Okay, so less repulsion, which implies that they are more stable. So the anti-form is the most stable form, and lesser than that is the Gaucher form, this one, or the staggered form. Lesser than that is the partially eclipsed, and the least is the fully eclipsed form. So here we are also done with conformational isomers, starting with aromatic hydrocarbons. So aromatic hydrocarbons. Now, what are aromatic hydrocarbons? They have a characteristic aroma. Okay, first point. And second, they have high carbon content. So these 2 points will include your definition of aromatic hydrocarbons. Now, there are three types: benzenoid, non-benzenoid, and heterocyclic. Benzenoid including benzene ring. Non-benzenoid not including benzene ring. Okay. Heterocyclic are cyclic compounds which have atoms other than carbon as well. So here are some examples. As you can see here, we have nitrogen as well in this full carbon cycle. We have one nitrogen atom, which is different from other carbon atoms, right? So, which is known as pyrrole. We have thiophene, right? Here it should be O, thiophene. Okay, so sulfur we are having in between. Again, we have nitrogen, but here, as you can see, it looks like benzene, but only one carbon is being replaced by N, that is nitrogen. This is pyridine. Okay, furan also we have. So these are all the examples. Now coming to aromaticity. So aromaticity, there are 4 conditions to prove that a compound or a hydrocarbon is aromatic or not. First is the cyclic one. Second is conjugation. Conjugation should be possible. Third is planar structure. So let us revise what is planar structure. That is sp2 hybridization. So here what does sp2 hybridization mean? It means that the H value, that is hybridization value, should be 3. Most easiest example is this BCl3. Okay, so why? Because 3 sigma bonds. So H value is 3. And when H value is 3, the hybridization is sp2, that is planar structure. Right? We'll get like planar structure. Right? No carbon atom, no chlorine atom is elevated or 90 degrees. This whole compound is on the plane. Right? Similarly, going for C2H4 ethene, consider 1 carbon atom, you will have sp2 hybridization for each carbon atom. Okay, now coming to the 4th condition. So the 4th condition is the condition that can confuse maximum of the people, that when to use 4n plus 2 or when to use 4n. Right? So let's clear them out with the help of questions. Right? So first question, taking the normal benzene ring. So of course, it satisfies the first condition, cyclic, conjugation done, planar done, right? Why planar? Because here you can see the structure. This is the structure that we'll get for each carbon atom, right? So coming to the 4th one. Now, what is the 4th condition? It is pi electrons. So what does pi electron means? Electrons involved in pi bond formation. So here, what are the pi bonds? Double bonds. So 1, 2, 3, 4, 5, 6. 6 pi electrons. So of course, 6 is greater than 4. I'll put it 4n plus 2 is equal to 6. So plus 2 will go that side. It would become minus 2. 4n is equal to 4. N is equal to 1. So n should be equal to whole numbers like 1, 2, 3, 4, etc. Okay. So here n is equal to 1, which implies that benzene is an aromatic compound or hydrocarbon. Right? Now coming to the next one, second one. Yeah, the second one is like, as you can see, we have 4 carbon atoms and we have 2 double bonds. So here we have how many pi electrons? 1, 2, 3, and 4. So here we can't use this equation. Why? Let's try using 4n plus 2 is equal to 4. If I put, then I'll get n value as half. Right? It is not whole number. So we have to put 4n is equal to 4. Okay? So we'll get the value of n is equal to 1. Now coming to some important things, that is the 3rd and 4th one. So here we have a triangular hydrocarbon with 1 pi bond, that is 2 pi electrons, right? So I have 2 pi electrons. Again, it is lesser than 4, right? So 4 or lesser than 4, we have to put 4 in that formula. Okay, so we'll get 4n is equal to 2, n is equal to half. It is not aromatic, it is anti-aromatic, right? So if I put this formula also again, that is 4n plus 2 is equal to 2, right? I'll get 2 because 2 pi electrons are there. Though I'll get n is equal to 0, which is not possible. Now, this is in the case of plus sign, right? You need to remember plus and minus also. Now, the 4th one is somewhat important. It is having minus sign here, right? We have the same 1 pi bond, that is 2 pi electrons, but we have a minus sign here, which implies that we have 2 more pi electrons. So the total pi electrons are 4 pi electrons. Minus sign implies the formation of 1 more bond, which includes 2 electrons, right? So we'll have here whenever minus sign is there, add more 2 electrons. Okay, so 4n is equal to 4 we'll have, right? That is 2 electrons from this minus sign and 1 and 2, right? So 4n is equal to 4, n is equal to 1. So it is anti-aromatic. Why? Because I use the formula 4n. When I use the formula 4n plus 2, it is aromatic. Okay. Now coming to methods of preparation of benzene. We are soon going to complete this chapter. Yeah. Methods of preparation of benzene. So we have only 6 methods. First method is aromatization of aliphatic hydrocarbons, right? So again aromatization Al2O3 in presence of heat. So I'll take CH3, CH2 4 times, CH3, why 4 times? Count the number of carbon atoms. 6 we want. Okay, 6 we got. Why? Because here 4 I have taken, so 4 carbon atoms, outside 2, 5 and 6, right? As well as hydrogen also you can match and see. You will get the perfect number. That is C6H6. H also I have here 3, 3, right? So we are also using Al2O3, you should remember. Now second one is polymerization. Also this is also a very common thing. So you need to remember polymerization comes, then it is the use of RHT, red hot tube, right? So 3CH triple bond CH in the presence of RHT, that is red in the red hot tube, will give us benzene, right? Third one is diazonium salt. Now what is a diazonium salt? It is any kind of salt which has R, that is alkyne, alkyl group, N2Cl. So we have N2Cl here, as you can see. Yeah. So this is the N2Cl group and we have R as this benzene group, right? So plus H3PO2, that is hypophosphorus acid, will give me benzene plus N2 evolution plus HCl, right? Then the third one done. Fourth one is benzene sulfonic acid. Sulfonic acid, SO3H. Benzene attached to sulfonic acid, right? Reacting with water, what it will give? Benzene plus H2SO4. Okay, these all are very simple, just you need to remember. Phenol, fifth one is phenol, that is benzene ring with OH. In the presence of zinc dust, it will give us benzene ring plus ZnO. Sixth one and the last one is sodium salt of benzoic acid. So this is the one we'll see. Yeah. So benzoic acid. So I'm using benzene like this and COONA plus NaOH in the presence of CaO and heat. It will give me Na2CO3 and benzene ring. Okay, so these are all the methods of preparation of benzene. Now, how we will remember these? Again, for this, we have one more shortcut, that is SPA, SBPD. Okay, so this sounds somewhat unique. Okay, so here, okay, so the first SB, okay, first talking about SB, it stands for sodium salt of benzoic acid. P stands for phenol. One P stands for phenol. Another P stands for polymerization. Okay. And one more S stands for sulfonic acid. A stands for aromatization and D stands for diazonium salt. So you can remember it like this: SPA, SBPD. Okay. Or you can create your own acronyms. Now coming to chemical properties of aromatic compounds, electrophilic substitution reaction. Okay, substitution reaction, electrophilic. Okay, so first one is, we have again only 5 reactions. So first is halogenation, in particular chlorination. Okay, addition of chlorine molecule, that is Cl2. Okay, so what we'll get? Benzene plus Cl2 in the presence of FeCl3 will get benzene ring attached with Cl, and another Cl will go with hydrogen, that is to form HCl. Second is nitration. Name only we can understand, HNO3, nitric acid. So benzene plus concentrated HNO3 in the presence of concentrated H2SO4, that is the dehydrating agent, it will give us benzene attached to the nitro group. Okay, plus H2O. Now coming to sulfonation, again H2SO4, benzene ring plus concentrated H2SO4 will give us benzene ring with the sulfonic acid group, okay, plus H2O. The fourth one is Federal-Kraft alkylation and Federal-Kraft's acylation, okay. So Federal-Kraft, when you hear this name, you should get to remember anhydrous AlCl3. Okay, so anhydrous AlCl3 is the reagent in Federal-Kraft's, whether it be alkylation or acylation. Okay, coming to alkylation, so here we have alkylation, right? So benzene plus CH3Cl in the presence of anhydrous AlCl3 will give me benzene plus one alkyl group, that is CH3 in this case, plus HCl. So here the electrophile is an alkyl. Okay, now coming to Federal-Kraft's acylation. Here, as you can see, benzene is reacting with CH3, C double bond O, Cl. So as we know, chlorine is the negative part, rest everything is the positive part. Whatever is positive, take it as electrophile, right? And reacting it with anhydrous AlCl3. So the positive part will be attached to benzene to give acetophenone plus HCl. Okay. So here we are done with the chapter hydrocarbons in one shot. We also discussed about the chemical properties. So I'll just show you. Yeah, chemical properties of firstly alkanes, remembering it with Safnik. Okay. And the next one is chemical properties of alkenes. So remembering it with HH, H2, H2O, oops. Okay. Then coming to the chemical properties of alkynes, right? Chemical properties of alkynes was only two, that is acidic nature and polymerization. Acidic nature is directly proportional to S character and electronegativity as well. Terminal alkynes are acidic in nature. Okay. So then we saw about double bond equivalent or degree of unsaturation. Then we saw conformational isomers or conformers. In that we saw firstly ethane, then propane, then butane. And in all three, we saw the Newman form as well as the Newman projection as well as the Sawhorse projection, right? Then we saw aromatic hydrocarbons, types of aromatic hydrocarbons, aromaticity. What are the four conditions of aromaticity? Some 4 questions on the aromaticity and methods of preparation of benzene. Okay, methods of preparation of benzene. Remembering it with SPA, SBPD. And then the chemical properties of benzene or aromatic compounds. Okay, so here we are done with the session and thank you for watching.